Membrane filtration, passing water through synthetic membranes to purify it, is a rapidly growing field in drinking water treatment. The vast majority of experience is in high-income countries, but increasingly membrane filtration is being adapted and applied in low and middle-income countries, and even at the household scale. In this module, we will discuss different types of membranes and how they are configured, how they improve water quality, and how they can be applied for household water treatment. There are several different kinds of processes involved in membrane filtration, which all have impacts on the quality of the filtered water. Perhaps the most obvious is a size exclusion phenomenon, where particles are strained out through either small pores in the membrane itself, or they're collected at a surface layer, a cake that forms on the surface of the membrane. A second kind of process, though, is an electrostatic process, where particles that have a positive or negative charge interact with the membrane surface. If the charge is the same, they will repel each other, and if the charge is opposite, the particles can be attracted to and absorbed on the membrane surface. Finally, membranes are biologically active, and that can have large impacts on the removal both of pathogens and dissolved compounds. Different types of membrane filtration can be defined on the basis of the pore size, or the size of materials that can pass through the membrane. Membranes with smaller pores will exclude more particles and even dissolved substances, but will require more pressure to force water through the membrane. First, you can think about simple cloth filtration. Most cloths have an effective pore size of around 100 to 150 microns, about the diameter of a strand of hair. Remember our cartoon of the sizes of different pathogens? Certainly viruses and bacteria can easily pass through cloth, and most protozoa as well. However, some pathogens are attached to larger particles which could be removed by cloth, including insect hosts. The guinea worm larvae, which is transmitted by copepods, little water insects around 1 millimeter in size, can be effectively removed with cloth filtration. Studies in Bangladesh have also shown that cloth folded over 4 to 8 times has an effective pore size of about 20 microns, and cholera is also transmitted at least partially through copepods, so studies have shown that the use of cloth filtration can reduce cholera by about half in Bangladesh. Sand, silt, and clay are inorganic particles that are defined by their size. Particles smaller than 2 to 4 microns are called clay. Particles up to about 63 microns are called silt, and particles up to 2 millimeters are called sand. After that, you get into gravel and boulders. Cloth filtration, then, can remove most coarse and medium sand, but doesn't do much for silt and clay, so turbidity may not be very much reduced by simple cloth filtration. But most membrane filtration uses synthetic membranes made of different plastic-like materials. There are 4 general types of synthetic membranes, which have different pore sizes and therefore operate at different pressures. Microfiltration membranes have pore sizes of about 0.1 to 5 microns and require little pressure to force water through the membrane. By the way, let's talk briefly about units of pressure. The atmospheric pressure at sea level is 100 kilopascals, which is commonly called 1 bar, or 1,000 millibars. Now, 1 millibar is roughly equal to the pressure caused by 1 centimeter of water, so 1 bar, 1,000 millibars, equates to about 10 vertical meters of water. 1 bar is also equivalent to 15 pounds per square inch, roughly, if you prefer PSI units. Now, microfiltration typically requires less than 1 bar of pressure. Since the pores are large, it's easy to filter water quickly, and you can typically get several hundred liters per hour from a square meter of membrane. Microfiltration will usually remove protozoa, like Cryptosporidium and Giardia, and depending on the membrane, may also remove bacteria, like E. coli and Shigella. Viruses and chemicals would not be removed, except the fraction retained on larger particles or adsorbed onto the membrane surface. Ultrafiltration membranes have pore sizes roughly from 10 to 100 nanometers, where 1,000 nanometers equals 1 micron. So these will completely exclude bacteria and larger particles, and may also remove viruses and larger molecules like proteins. Ultrafiltration membranes require more pressure, typically around 1 bar, but up to several bar. Flux is dependent on the operating pressure, but can typically be around 100 liters per hour per square meter. Nanofiltration membranes go from about 1 to 10 nanometers, so they should completely exclude all pathogens, including viruses, as well as larger molecules having molecular masses from about 200 to 1,000 daltons. Divalent metal cations like magnesium, which cause hardness in water, can also be excluded by nanofiltration due to electrostatic effects. So these membranes are often used for water softening. Operating pressures can go up to about 10 or 15 bar. Finally, the tightest membranes are called reverse osmosis, or RO, which can remove pretty much any kind of ion. RO is used for desalination, but requires very high pressure, up to 80 bar. Membranes come in several different configurations. The first main configuration is flat sheets, like sheets of paper, which can be mounted on racks or can be wrapped around a spacer in a spiral roll. The second main class is hollow fibers or tubes, where water is passed either through the inside of the tube and collected on the outside, or from the outside and then collected on the inside. In both cases, one of the objectives is to maximize the surface area of membranes that can be packed into a treatment module, so you also maximize the amount of water that can be treated for a given size filter module. Membranes can also be operated in a dead end or cross-flow configuration, where dead end means that all of the water is put on top of the membrane and pushed through the membrane. In contrast, cross-flow, the water passes laterally across the surface of the membrane, with some of the water permeating through the membrane to the clean side where it's collected. Perhaps the greatest challenge of membrane filtration is that of membrane fouling. A clean new membrane will process a lot of water with relatively little pressure, but with time, particles build up on the surface. A layer forms, a cake layer, especially if the membrane's operated in a dead-end mode. And internal to the membrane, particles can lodge in pores, or dissolved compounds can adsorb and restrict pore size. So over time, flux decreases, and you need more pressure to get the same amount of water through the system. The response to this is to do regular backwashing, reversing the flow of water to remove some of those particles, especially from the surface, or to pass water across the surface in a cross flow at a high velocity to scour it. And that can remove what's called the reversible fraction of fouling, but typically there's still some irreversible fouling that remains. That can be removed in part, but not wholly, by cleaning the membrane with solvents or with acids or bases, depending on the compounds causing the fouling. There are many examples of household application of membrane filtration in high-income and middle-income countries. Typically, reverse osmosis or nanofiltration systems could be installed in the kitchen. They would require electricity and usually an additional pump to generate the pressure to pass water through the membranes. However, there's increasing development of applications using ultrafiltration or microfiltration membranes that use less pressure to treat the water and can even be applied in some cases without electricity in low and middle and income settings. One of the best known examples of these schemes or these technologies is the LifeStraw family, which is produced by Vestergaard Franzen. The LifeStraw family, here you see their LifeStraw family 1.0 model. It uses an ultrafiltration membrane with a 20 nanometer pore size, which is small enough to exclude protozoa, bacteria, and also viruses. It's operated in a dead-end mode using hollow fiber membranes, where the membranes are found in the blue cartridge here, and you simply fill the blue reservoir with raw water to be filtered. There's a hose that connects the reservoir to the filter, and it's about 1 meter long, so that provides the pressure necessary to pass the water through the membrane. The system includes a red bulb for manual backwash, and it can produce about 9 liters of water per hour, with a lifetime of about 18,000 liters. The system also includes a halogen compartment where a chlorine tablet can be put, and this isn't for removal of pathogens as much as for preventing of membrane fouling and minimizing the need for backwashing. Vestergaard has been producing LifeStraw filters since 2005, first in emergencies such as earthquakes in Haiti and Pakistan, but increasingly has been targeting household routine use. And one of their largest experiences to date has been in Western Kenya, where 880,000 of these LifeStraw 1.0 family filters were distributed. In subsequent models, we'll look more at their business model, but here we're focusing on the technologies. Vestergaard has recently developed a second-generation LifeStraw family filter, the LifeStraw 2.0, which has a similar membrane to the 1.0, though it does include an 80-micron pre-filter. One of the big differences, though, is that the 2.0 includes reservoirs, both a 5-liter raw water vessel, dirty water tank, and a 5-liter reservoir for filtered water, which can minimize the potential for recontamination after passing it through the membrane. It's a bit larger as well, so it has a 30,000 liter lifetime compared to 18,000 for the 1.0. One large application of the LifeStraw family filter is as part of the Del Agua Health Program being implemented in Rwanda. And this is a combination of the LifeStraw 2.0 along with improved cook stoves to reduce indoor air pollution. They're targeting 600,000 poor households throughout the country. The LifeStraw family is a well-known application of ultrafiltration modules at the household level in low and middle-income countries. But it's not the only one. Here you can see some other examples of microfiltration products. Katadyn, primarily targeting backpackers and sports enthusiasts. Nerox produces a microfilter that's used in emergencies, as does Sawyer. And then there are a number of ultrafiltration products out there. One which my institution, EAVAG, has been developing is a gravity-driven ultrafiltration membrane, which is a slightly different approach in that we allow a biological layer to develop on the surface of the membrane, so there's no need to do backwashing or cleaning. And if you'd like to hear more about that, visit our website. Then Lifesaver Systems has a bottle and a jerry can version, Polymem, and you've seen the Vestergaard Franzen system. Membrane filtration, like all treatment processes, has advantages and challenges. One of the main advantages is that the membrane provides an absolute barrier to particles as long as system integrity is ensured. Most of the membranes can exclude protozoa and bacteria easily, and the tighter membranes can also exclude viruses. However, the looser membranes, such as microfiltration and ultrafiltration, have little effect on chemicals directly, though some chemicals may be removed along with the particles or can absorb onto the membrane surface. Membrane filtration can be very simple to operate, though there is a need for backwashing and cleaning. One advantage is that membrane filtration doesn't change the taste of the water, though it does reduce turbidity, which consumers often appreciate. However, membrane filtration doesn't provide any residual protection against recontamination, so especially if there's not a safe storage container, they're vulnerable to recontamination. Some of the membrane filtration models require electricity or high pressure, and for all of them, supply chains are necessary for the initial purchase, but also for replacement parts and services. So in summary, we've looked at membrane filtration as one type of this second class of treatments, filtration, which could be followed by disinfection and then safe storage. We discussed cloth filtration and how the pores in cloths are quite large, so the cloth is useful for removing large particles, including copepods, but not smaller ones, such as bacteria or viruses, and spent more time looking at synthetic membranes, especially these 4 types of membranes: microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, defined on the basis of their pore sizes and operating pressures, and we saw which membranes could exclude which kinds of particles and dissolved compounds. Finally, we concluded with a brief summary of the advantages and challenges of membrane filtration.